So
Okay.
yeah, we should start.
Okay, so it's a pleasure to have Nisheeta Desai giving us this condensed matter seminar. She's done some extremely nice work with Ribu Kaul during her thesis, coming up with a general strategy for designing spin S quantum spin models, which are sign free in their quantum Monte Carlo simulation and have interesting phases that other people have been speculating about earlier. And her method allows her to realize some of these phases. So today we'll hear some of this. Nishita went to Ribukol after a master's at BITS Goa, and she actually was a part of DTPTIFR doing her master's project with me at that time. So it's a pleasure to have her back.
Thank you. So I'm going to talk about quantum phases and phase transitions in designer spin models. The talk is based on these two papers here. So the work was done with Raghu Kaul at the University of Kentucky. So I'll start with a short introduction to
Can
quantum.
you go full screen?
Yeah. Sorry. Yeah. So I'll start with a short introduction to quantum spin models. So here I've just shown some simple basic standard definitions of, say, the Heisenberg model, the spin operators, and the spin half operators, Pauli matrices. So I'll start by describing why this problem of quantum spin systems is a hard problem. So here, the Hilbert space of a quantum spin system is a tensor product of local Hilbert spaces of spins at each site on a lattice. So if I have just if I have just one spin half, then the Hilbert space is 2. But if I have, say, ns number of spin half sites, then the Hilbert space grows exponentially. It is you have 2 to the ns states in the Hilbert space, and a Hamiltonian is an exponentially growing matrix to diagonalize. So now, if you have just two sites, as an example of a Heisenberg interaction between just two sites, it's a 4x4 matrix to diagonalize, and you get 4 eigenstates. If J is greater than 0, that is, if you have the antiferromagnetic interaction, then the ground state is a singlet ground state with a total spin of 0. So now this was just for 2 sites. And in a real material, you in general have Avogadro number of particles, right? And you want to go to the limit of ns tends to infinity. Now we saw for ns equals 2, 2 to the ns, which is 4. But if you go even up to 30 sites, it becomes a billion by billion matrix to diagonalize. So you see how fast it grows. So and that's why you can reduce the dimensionality using some symmetries, but even then, numerical diagonalization is prohibitively expensive for when the number of sites is more than 40. And this is just for spin a half. If you have higher s, it's even fast. The growth is as 2s plus 1 to the ns, so that's even worse. So now I'm going to talk about some well-established results in quantum spin systems, starting with one dimension. So spin half Heisenberg chain is a very famous example. It was solved by Bethe in 1931 using the Bethe ansatz. So he solved the nearest neighbor Heisenberg chain. He solved for the full spectrum of the Hamiltonian. Now, what is the ground state of this model, right? So we saw that when J is greater than 0, two sides, the ground state of two sides is just a singlet. So you might think that each spin tends to form a singlet with a neighboring site, and that forms long-range order. But Bethe found that this model actually has gapless excitations. But we also know from Morman-Wagner theorem that you cannot break a continuous symmetry spontaneously in one dimension. So you cannot have long-range magnetic order either. So the ground state, as it turns out, is a critical state where all correlations decay as a power law, not just the spin-spin correlations, but even the dimer-dimer correlations decay as a power law in the antiferromagnet. So now that was the case for the spin half Heisenberg chain. One might think, what happens to the spin one Heisenberg antiferromagnet, right? So since it's a higher spin. You would think it's more classical and it has more tendency to order. But what the spin 1 Heisenberg antiferromagnet does is that it's completely disordered. All the correlations are exponential. There's a gap to excitations. And it also exhibits these spin half edge states. So the way to understand this this wave function or the state is that you think of each spin as two spin halves. At each site, you replace each spin 1 by a symmetrized wave function of two spin halves. And then each spin half forms a singlet with a neighboring spin half, like it's shown here. So this construction was initially given by Affleck, Kennedy, Lieb, and Tasaki. And they gave this, this wave function as the exact ground state of not the Heisenberg model, but a different Hamiltonian. This is the Hamiltonian where you have a projection on total spin 2 on two neighboring spin 1s. And the ground state of this model is the AKLT state that I showed in the previous slide. So although this is the exact ground state of this other Hamiltonian, it was shown numerically to be also the ground state of the Heisenberg antiferromagnetic chain. So these were some examples of exact solutions. There have also been some field theory predictions. For example, Haldane gave a field theory prediction for spin chains, and he also got the Nobel Prize for his work on spin chains. So he predicted the long distance behavior.
Nisheeta, a quick
Sorry?
question. When you say this is also the ground state of the Heisenberg model, you mean it has the same correlations,
Yes.
but not the exact same wave function? Right?
Not the exact same wave function.
So you're saying state in the same sense as we say phase of matter.
Yes, phase of matter, right. Yeah. So so the long distance behavior of quantum spin chains was given by these field theory arguments. So Haldane predicted that for half integer spins, you have a gapless state and correlations of power law, while for integer spins, you have a gapped state with exponential correlations. And this proposal has been verified in a number of ways. There are a number of results that are consistent with this proposal. So there are a number of theoretical results like bosonization, conformal field theory, there are numerical results from DMRG. Then there have been experiments on real materials that are also consistent. So this is a well-established result in one dimension. Now, given this,
One question.
yes.
The experiments that you're talking about, they're on S equal to 1 or S equal to half or 3/2?
Okay, so yes, this copper sulfate is spin half. And the second material here, that is spin 1.
I see. Okay.
So given this well-established result in one dimension, one might ask what happens in two dimensions, right? What is the role of the spin plays in two dimension in determining the quantum phases? So this question is harder in two dimensions for a few reasons. In two dimensions, the exact solutions are very rare. DMRG is a very powerful method in one dimension, but it cannot be extended as well to two dimensions. It works only on systems of moderate size, so you can't extrapolate the behavior to infinite size very reliably. Quantum Monte Carlo is a very reliable technique, is the most reliable technique, but it has a drawback. You can only simulate models that have a sign that don't suffer from the sign problem. And I will talk about that later. Before that, I will talk about some well-established results in two dimensions now. So now,
one more question.
Yes.
There's always 2D versions, people like PEPs or Tensor. They
Yes.
also are only restricted to moderate size, or they can go to larger size?
So as far as I understand, PEPS is also a tensor networks technique, right? Yeah. So they have they cannot access as big system sizes as we can in Monte Carlo.
I see.
So here is the Heisenberg model in 2 dimensions, again, doesn't have an exact solution, but from some approximate.
Nisheeta, just to
Yeah.
follow up on that,
Yeah.
if they assume a fully translationally invariant solution in the tensor network calculations,
Yeah.
then presumably size is not so much a limitation as the internal dimension, right, of the tensor network.
Uh-huh. I see. You mean the bond dimension?
Yeah, I mean the bond
Oh,
dimension.
okay. I
Because
see.
there's a systematic error that they make, and they can get completely wrong answers if they have a smaller bond dimension. So
I
presumably the
see.
limiting
Mm-hmm.
feature there is the bond dimension, right?
I see. I see. That is probably right because I've done DMRG on some
Yeah,
one-dimension
that involves
cases.
finite size because you do this snake DMRG, right?
Yeah. Yeah.
Finite
So
size DMRG. Yeah. So
there.
that what you're saying is correct, I guess, based on your experience with that snake DMRG.
Mm-hmm.
But if you do one of these translationally invariant tensor product states,
I see.
then presumably the problem there is that there's a systematic error having to do with bond dimension and convergence,
Mm-hmm.
which is very hard to fix.
I see. Yeah, I've faced that while simulating gapless phases.
Yes, exactly, for gapless phase.
Oh, right.
Yes,
Yeah.
yes.
Okay.
Nisheeta, just a simple clarification. So,
Yes.
are you talking about the zero temperature case? Is it, or is it
Yes.
finite temperature?
This is the zero temperature. At zero temperature, it's a ground state that dominates the physics, right? So when
When you
I'm
say exact solution, you mean the full spectrum to
the full
determine.
spectrum. Yes.
Okay, thanks.
Yes. Um, so yes, this is the Heisenberg model 2 dimension, which has only approximate solutions. And we find that it's nail ordered for all possible spins, doesn't matter what the spin is. This is in contrast with the 1D case where the value of the spin affected the ground state of the model a lot. But now in 2 dimensions, the value of the spin actually determines what kind of quantum phases are possible. That is, if you disorder the nail phase using some quantum fluctuations, uh, you can have a phase transition into a quantum phase, and what kind of phases are possible and what kind of transitions occur, it depends on the value of the spin. So an example is this transition. In case of spin half, you can have the valence bond solid phase. Here you can see each spin forms a singlet with a neighboring spin, and this pattern of singlet forms long-range order. And so if you do a standard Landau-Ginzburg analysis of this phase transition, then you would think that since these two phases break different symmetries, the Phoebius phase breaks translational symmetry and the nail phase breaks spin rotation symmetry. So, if you do a standard analysis using Landau-Ginzburg techniques, you would think that the transition between these two phases is generically first order. But there has been a theory that propose that you can have a transition where the order parameters of both the phases continuously go to zero at the critical point. And this is the celebrated deconfined critical point. So this was a theoretical prediction, which was verified uh, by verified, I mean there is a lot of strong evidence in favor of the second order scenario. Um, so although there are many scaling corrections to this transition, there has even on the biggest system sizes there have been there's no conventional evidence of first order behavior that has been found. Um, so that is the spin half. That's a phase transition, a quantum phase transition in case of spin halves. That is unconventional. And this is one particular field theory that has been provided. So the original field theory was not in terms of the order parameters of either of the phases, but this is an alternative field theory that is in terms of the order parameters, and that's why I'm showing this. I'm not an expert in this field theory, but I'm just sketching it out because it's related to what I'm going to talk about later. So here you have a super spin, a 5-component super spin. So super spin has 5 components, and the first three components are the Nail order parameter, the three components of the Nail order parameter, and the last two components are the two components of the VBS order parameter. And so the action is given by a nonlinear sigma model in this super spin. So here you have the nonlinear sigma model, the first term. The last term is a topological term. And in the middle, you have these anisotropies. So these OIs are some anisotropies which break the SO5 symmetry of the nonlinear sigma model. And what they do is that they favor either the nail side or the VBS side. So the proposal was that if there is one leading anisotropy that drives this transition between the nail and the VBS phase, and all the higher anisotropies are irrelevant at the critical point, then there's an emergent SO5 symmetry at the critical point. So this prediction has been verified in some numerical simulations. Some people simulated 3D classical loop models, and the phase transition in those loop models has been shown to be in the universality class of the nail VBS transition. And they showed an emergent symmetry between, they showed some evidence for emergent symmetry between these order parameters. So now that was the story for spin half. In case of spin one, you can have even more interesting quantum phases. Apart from the columnar valence bond solid phase, you can also have what we call the Haldane nematic phase. This phase is a direct product of AKLT chains in either the X direction or the Y direction. So you can see that this phase breaks the rotational symmetry of the square lattice and keeps the translational symmetry intact. And this phase was theoretically predicted in 1990. And now a number of studies have tried to investigate this phase because it's proposed to be a normal state of a high temperature superconductor iron selenide. And that's why it has triggered a lot of interest. So our motivation for studying this is trying to study this phase was the possibility of a continuous phase transition between the nail state and the Haldane nematic state. So again, there was a field theory proposed, just like the super spin nonlinear sigma model field theory for the spin half case. Here again, there was a similar field theory, but here the super spin had 4 components. The first 3 being the 3 components of the nail order parameter again, but the fourth one is the Ising-like order parameter for the Haldane nematic phase. So they propose that if you have an O3 cross Z2 anisotropy that drives this transition, at the critical point, you would have an emergent O4 symmetry between all the components of this vector. So we were trying to verify this proposal of a possible exotic continuous transition with emergent symmetry. And to verify this with quantum Monte Carlo, we need a sign problem-free model. So that is a designer spin model. Designer spin model is a model that has been constructed to not have the sign problem, but it also hosts interesting ground states. So this is where our work comes in. We try to design a model that realizes the Haldane nematic phase. So now I'll talk a little bit about quantum Monte Carlo and how the sign problem comes in our case. So this is just a small introduction to Monte Carlo. You have a physical system with a number of configurations. Each configurations have some weights, and you're trying to sample the configurations with corresponding probabilities. Now in quantum Monte Carlo, you have a d-dimensional quantum problem, and you map it to a classical problem in one higher dimension. Now, when you do that mapping, sometimes the weights become negative. And when there is no way to do this mapping in such a way that all the weights are positive, then we say that the model has a sign problem.
So, just one question.
Yes.
In this designer Hamiltonian that you are going to, let's say you get a phase like this, How far does it tell you about either the original film theory or the material system to that extent?
The original. So what we are trying to do is we want to find some generic features near the phase transition. So it doesn't need to the original material doesn't need to have the same model, but what we want is the access to the phase transition.
Right. And so you're saying that you will get the same universality, so then you don't care.
Yes,
But
yes, yes, yes. Yeah.
yeah, go ahead, please. Sorry.
Okay. Yeah. Thank you.
So how well founded was this proposal for a O4 transition? Do you have an opinion on that?
Uh, so I'm right. So I'm not exactly an expert with field theory. So uh, I don't. But it was done by some
I mean, do
very
they? No, no, that's okay. I'm also not an
yeah
expert in field theory,
yeah.
but do they mention some caveats,
Uh,
or do they make a strong claim that this transition must be like this?
they don't. Yeah, I'm not sure of whether they. The
Because
thing
the
is,
O5 symmetry
mhm.
proposal, there were caveats, right? They didn't insist that it has to be
Yes,
like that.
yes,
There was a
yes.
controversy about it for a while and so on.
Uh-huh.
And only the numerical work finally said, yes, it's happening.
Yes, yes. So I guess, yeah, unless you have a microscopic model that
Yeah, so I guess it
studies,
was not
yeah,
entirely obvious what the
yeah,
transition would be, right? In spite of their proposal.
yes, yes, it's not obvious.
Okay.
Yeah, right. So yeah, this is how we do the simulation. This is our partition function. This is a quantum partition function, and we write the trace as a sum on a complete set of states, and we expand the exponential out into a series, and now we have a series expansion, and we want to sample each term in the series. So each term in the series, you can show it maps to a classical loop model in one higher dimension. So here I've shown a picture of a spin one chain uh, with, and the basis is the SZ eigenstate at each site. So you can see that if you have a one-dimensional spin chain, it maps to a two-dimensional classical loop model. And the extra dimension is what we call the imaginary time direction. And there is periodic boundary conditions in this imaginary time direction. So these are a set of configurations which have a certain weight. And these weights are proportional to the matrix element of this operator of the operator minus beta h to the n. And what we want for each configuration to have a positive weight is we want the matrix elements of H to all be negative. So now, what are the Hamiltonians that satisfy the sign problem-free condition, right? One Hamiltonian is the Heisenberg antiferromagnet. So if you take the Heisenberg antiferromagnetic exchange, here capital S here is the value of the spin. And the reason I've subtracted S squared here is so that this whole quantity in the bracket is positive. I mean, all the diagonal elements of this quantity are positive. And now you can see that if you do a unitary transformation on either I or J, you get all the off diagonal elements can also be made negative. So there is that basis where this model does not have a sign problem. And this model does not have a sign problem on a bipartite lattice because on one bipartition of the lattice, you can make this unitary transformation, and that's what makes the model sign problem free. So in the spin half case, all the sign free models that have been constructed for spin half have been from products of H2IJ on one bond, on two bonds or more than two bonds. So since H2IJ is sign problem free, its products are also sign problem free. So that's how we get sign problem free models for spin half. And so now you can ask, how do you get sign problem free models for for higher spins, right? Is there one way is just take a product of H2IJ on more than one bond, just the way we do for spin half. But our question was, is there a more general set of models for spin S? The answer is yes. And the way you get more general set of models is by taking help of the split spin representation. So in the split spin representation, you write each spin S as a sum on 2S spin halves. And once you write your Hamiltonian in terms of spin halves, you have a spin S Hamiltonian, you write it in terms of spin halves, you want to project on to the total spin S subspace. And that's why you have this projection operator, which is actually a symmetrization operator. You have a product of local symmetrization operators at each spin S site. That's what. So this is now the partition function that we want to simulate, where we have replaced all the spin s's by spin halves, and we've put a projection operator at the last time slice. So now what the projection operator does is that it acts as a modified boundary condition. So you can see that if each of these rectangular blocks is one spin one site, and it has two spin halves. So as you propagate in the imaginary time direction, if you have two up spins, these full circles are up spins. And if you propagate in the imaginary time, the up spins go to up spins. If you have a down up, it may go to an up down, or it may go back to itself with equal probability. So what the permutation operator does, what the projection operator does is it makes sure that the spin state comes back to itself in the imaginary time direction, but up to a permutation of up and down spins at each site. So yeah, this is how we simulate a spin S model in terms of spin halves. Now you might ask, why are we simulating a spin S model in terms of spin halves? So there are two advantages of doing this. One advantage is that it makes our simulations much more efficient. In case of spin halves, you have some deterministic loop updates that makes everything much more efficient. And another reason is that it tells us a big advantage. And the reason we did this is it tells us what models are sign problem free. And I will explain that with some pictures. So here,
Nisheeta, before you go to the advantage in terms of constructing new kinds of models, which
yeah.
is of course very interesting,
Mhm.
this point that you noticed in your thesis about better efficiency,
Yeah.
that's also something very interesting which I have not fully understood. Can you elaborate on that very briefly?
Right.
It was
So,
not a priori obvious to me before your work
uh-huh.
appeared that it would be more efficient. Can you just clarify that a little?
Right. So in now generally when you have a higher spin model, you have probabilistic updates, right? Uh, you need to solve some directed loop equations, and when you do the loop updates at each operator, you have some probabilities.
Yes.
So that
Also,
is
you are saying you can have a deterministic Swenson-Wang kind of breakup in this case. Is that
yes,
the point?
yes, and the only non-deterministic part comes from these
The
projection.
projection operator.
Yes.
So the efficiency comes because you localize all the things that depend on a random number generator in one layer.
Yes.
I see. Okay.
Yes.
Thank you.
Right. So now I'll talk about how these models are more obviously sign problem free in this spin half language. So this is a spin one Heisenberg model. The S dot written as S dot S minus one. I've subtracted the one to make it sign problem free. So now when I can write down this Heisenberg model in terms of the spin half operator. Let's say
Hi, Kedar. Yeah, I actually didn't understand why in one dimension putting the random number it will be efficient. So Nisheeta, could you
uh-huh.
please?
Sorry,
uh,
I didn't hear that.
uh,
You're asking her, right? Not me, right?
Yeah, yeah. Sorry, yeah, to Nisheeta. Yeah.
right. So in the previous case, you have all these operators at each time slice, and you could have different probabilities for different loop moves in each operator. But now you have a non-deterministic part only at one time slice. Instead of at every other time slice, it is deterministic, and it's only when you encounter these projection operators is when you encounter a probabilistic move.
So I think maybe Nilmani doesn't know exactly how stochastic series expansion
Okay.
works. That's so the
Uh-huh.
point is,
Yeah.
Nilmani, what you have to do is you have to go through the whole operator string, and in the usual procedure that she's talking about, you would need to throw a coin at each time step. Here
Yeah.
she has to throw a coin only once in the whole operator string.
I see. I see. Okay.
Yeah. Yeah.
Okay.
Thanks. So right. So here I wrote the Heisenberg model in terms of the spin half. So here the capital spins are the spin ones, and the little s's are the spin halves. Now let's look at this pictorially. Here, each of the gray bubbles represent a spin one site, and at each spin one site, I have two circles representing two spin halves. And this line here, this black line here, joining two spin halves is this 1/4 minus s dot s operator. So now if you look at this equation here, um, you can see that it requires you to draw these black lines between all possible combinations between these pair of spin one sites. So once you add up all of these four terms, this is what this is each term in this sum. So this is how we wrote down the spin one Heisenberg model in terms of the spin halves. And this was an easy example because we knew that the spin one Heisenberg model was already sign problem free. And looking at these pictures also, it's clear that it's sign problem free because you can write in terms of 1/4 minus s dot s, which is a sign problem free model. But now, if you look at a more complicated term, like this is the biquadratic term, which is s dot s squared minus 1. And this was not obviously sign problem free. It took a lot of work went into it to show that this was sign problem free. But now, once you write it in terms of these little spins, then it's just a sum on these two terms. And now again, you can see that's a product of 1/4 minus s dot s on two bonds on the same side, and that is obviously sign problem free. So you can see that in the language of the spin halves, it's much easier to tell that a model is sign problem free than in the language of the bigger spins than in the language of the actual spin ones. So we use this idea to construct our designer spin models. What we do is we first write down a model in terms of spin halves. And once we do that, we know that this model is sign problem free. So we can walk backwards, find the original model in terms of the original spin ones or spin s, and then we know this model can be simulated without a sign problem. So this is the example. This is the first model that we constructed this way. This is a 3-spin interaction. Here, these black lines again depict the 1/4 minus s dot s interaction. And now now at one site, you need the two spin halves to appear symmetrically. Otherwise, it won't be a valid spin one model. So that's why you have to add all of these terms where you have all kinds of combinations of spin halves between between a pair of sites. So now this is a completely new interaction. And when I write it in terms of the spin ones, it looks something like that. Now, if I had just written down this model, H3, what I call H3IJK, there is no way of telling that this was a sign problem-free model. But since I went through this route, I wrote the model first in terms of the spin halves. I know for sure that this model is sign problem-free. So this was our idea. This was I explained this for the spin one case, but you can generalize this to any spin straightforwardly. So now I can show some applications of this procedure. So the first application is what was getting the spin 1 Haldane nematic phase. So this is our H3 IJK interaction that I introduced earlier. And we constructed this model where we construct a plaquette model where we take this 3-spin interaction, we take a product on 3 rows, and we add that to a product on 3 columns. So now, the reason we want the product on rows and columns is because we want to maintain the 90-degree rotation symmetry of the square lattice, which we expect this phase that we want to find breaks the rotational symmetry of the square lattice spontaneously. So so this is the model that we want to study. This is the plaquette interaction, and that's the nearest neighbor Heisenberg interaction. And we want to increase the strength of this plaquette interaction and study the transition into the Haldane nematic phase. So this is, I'm just defining some order parameters. The M here is a staggered magnetization. Here are the order parameters of the VPS and the Haldane nematic phases. So for that, we need to define the bond operator. So suppose the BI is the bond in the I direction. And so I just take the dot product of the spins, of the 2 spins on that bond to get the bond operator. And so the VPS order parameter is the Fourier transform of Bx at pi0 momentum. And the Haldane nematic order parameter is the sum on Bx minus By. It's an Ising-like order parameter, so there can be 2 states. If you see long range order in this quantity, then that means we are in the Haldane nematic phase. So these are the order parameters, and now I'm going to show the phase diagram that we got. So here we find that the phase diagram has on the x-axis it's the coupling G, which on varying you get a transition from the nail phase to the Haldane nematic phase. On the y-axis I have the temperature. So at 0 temperature I have nail order, and since nail order breaks a continuous symmetry, it disorders as soon as you turn on temperature. And the Haldane nematic breaks a discrete symmetry. That's why it survives at finite temperature. So here, all of these are finite size extrapolations of the order parameters. So you can see wherever in the nail phase, the m squared extrapolates to a finite value at infinite system size, and in the nematic phase, the psi squared extrapolates to finite value. And in the inset here, I have the extrapolation of phi squared, which is the VBS order parameter. And the VBS order parameter can be seen to 0 in this entire phase diagram. So that means there's no VBS order anywhere in this phase diagram. So now what I do is I study the phase transition, different phase transitions in this phase diagram. So the first phase transition I study is along this blue line here. It's a finite temperature phase transition. So I go from the Haldane nematic phase to disorder. And the first thing I look at is the histograms of the Haldane nematic order parameter psi. And I see that at high temperature, I have just one peak at 0 psi, which corresponds to disorder. And as I lower the temperature, I see 2 peaks forming, and these 2 peaks correspond to the Haldane nematic order forming in either the x direction or the y direction. So now from these histograms, at least there's no evidence of a first order transition, but we also see that the order parameter shows a very nice scaling collapse along this transition, and the scaling collapse is at Ising critical exponents. So that is another confirmation that this phase is a Z2 symmetry breaking phase that we expected. So the other transition we study is the transition between the nail and the Haldane nematic transition. And we see from the histograms that we have two peaks at the transition, one at disorder and one at finite order parameter. And these histograms, these double peaked histograms get sharper and sharper as we increase the system size. And so this is evidence for a first order transition. And so at least in this simulation, we could not verify the claim of a possible continuous phase transition. It is possible that some other model might have a continuous phase transition between these two phases, but at least with these results that we have right now, there is no way to tell. So that is one example. So that's one of the transitions that we studied for S equals 1. And another transition that we studied was the nail valence bond solid transition in the square lattice. So in the nail BBS transition, in the spin half model, we saw that the model shows the model is presumed to have a continuous transition. But here now we want to contrast it with the spin 1 case. So in the spin 1 case, this is the model that realizes the BBS phase. This is the biquadratic model. I showed before that the biquadratic model did not have a sign problem. So I take the biquadratic model, I take the product of this term on two bonds on a plaquette, and I do the same. I take the 90-degree rotate version of the same
So,
term.
Nisheeta, if I
Yes.
just had the biquadratic term, that has an extra SU3 symmetry, right?
Yes, that's right.
So by putting the bilinear term, you are breaking that down to SU2 and studying.
Yes, exactly.
Okay.
Yes. Right. Right. So we supplemented with the Heisenberg term, which is SU2 symmetry. And now what we want to do is we want to study this transition as a function of G. So we find here I've plotted some ratios, some dimensionless ratios that go to 1 in the ordered phase and 0 in the disordered phase. And so they show a crossing at the critical point. So from these crossings, we can find the critical point between these two phases. And we find that this is a direct transition. And we find this critical point. And then we look at, or the transition point, and we look at the histograms of these order parameters near the transition point to find out what is the nature of this transition. So again, in this case, we see a first order transition. We see very clear double peaked histograms, but that becomes sharper with system size. So this is another way of looking at it. You look at the magnetic and the BBS order parameters in the Monte Carlo simulation, and you see that the system switches between the magnetic phase and the BBS phase, and that is what is characteristic of a first order transition. So here again, we see that in the spin half case, where this transition was this transition showed no evidence of a first order transition on the biggest system size studied. The biggest is, I think, 512 cross 512. But here, even at 48 cross 48 system size, you see very clear evidence of a first order transition. So again, I can't make any strong statements that this is a generic feature in spin 1 models, but we have a hypothesis that this is how the value of the spin affects phase transitions in 2 dimensions. Again, this might not be a generic feature; it might be just a feature of this model. Yeah, we need to study more models to make a strong conclusion. So yeah, this is the summary slide. I'll just keep this up, and thank you all for your attention. That's all I have.
Thank you. More questions?
So, Nisheeta, do you have any plans for what you suppose you?
Rajdeep, I can't hear you for one. Can you?
Can you hear me?
Now I can.
Now I can hear you. Yes.
Okay. So I was just wondering if you are coming to TIFR as a postdoctoral fellow, do you have any plans of what you would like to
Yes.
study? Yeah.
Yeah. So there, I have a number of ideas for what kind of models I can simulate that might realize uh, a second order transition for higher spin models. So that is one of the things that I want to study. Um, so, for example, there is, like Kedar said, there's the SU3 symmetric model, and the SU3 symmetric model actually shows a continuous transition. And I was thinking of I was thinking of adding a small SU2 term as a perturbation and checking if the model still remains continuous. So I think that is the best.
That
Um,
would be very illuminating, I guess. It might
yeah,
help us understand this controversy between
yes.
people who claim there is no such thing as deconfined criticality and
Mm-hmm,
people who are
mm-hmm,
convinced there is deconfined criticality, right?
uh-huh,
Yeah,
yes.
that's a good idea. Actually, I hadn't thought of that.
Uh-huh. And one can do the same, one can carry out the same study for spin 3 halves. Um, that is
Uh-huh.
one more thing I want to do.
Right.
Then also, Kedar had an idea of studying the transition between Haldane nematic and the VBS phase. So that is one thing I'm interested in.
Yeah, that would be interesting too. Yes,
Yeah.
I'd forgotten that. Yeah, we had talked about that, right?
Yes. Yes.
Yeah, yeah, good. And in terms of where this fits in, I guess the question is in this field theory thing, if they don't explicitly mention any caveats,
Mm-hmm.
the fact that you're getting a first order transition suggests that they're missing something basic, right?
Hmm.
They need to at least identify some term that can lead to a first order transition, and then
Mm-hmm.
it becomes a matter of detail whether that term has a coefficient of the right sign and enough magnitude to drive that. But
Yes.
if they don't mention any caveat of that kind, then it's not clear what they were doing, because you've got very
Hmm.
clear evidence for a first order transition.
Right.
So I guess there is that question. Somebody who's more field theoretically inclined than either you or me should go back in light of your results and look at that.
Hmm.
Yeah.
Yeah.
Where there are people in DTP who might be interested, but certainly I don't have the expertise for that.
Hmm.
All right. Any other questions? I guess if not, we can thank Nisheeta again for a very nice talk, very illuminating talk. Thank you. Uh, and I guess we can close the meeting.